So what if I had, oh, right, last time someone, was it here that someone asked about dominance? Yeah. Okay, yeah, okay, all right. So we did kind of talk about limits like this. Right, we've definitely done this kind of limit to infinity where you can see that the degrees are the same, and so the limit's going to be 1/3. And you can either show some work or not. And the work you would show would be dividing everything by x squared. I don't feel like we need to repeat that, but I certainly could show it if you guys want me to. Yeah. So I'm going to do something in. So I would love to see. I'm going to work on trying to get more kind of interaction on Zoom here. So I'm going to change the messaging so that you can only privately message me, so that you can only message me, that you can't message anyone else. At least I think I'm going to, but now I'm like, can I actually do that? Participants can chat with host and co-hosts. So I believe now if you send a message, I should be the only one you can see it. I think. Well, somebody send me, so yeah, okay, cool. Yep, right on. So nobody else can see your answers. Only I can see what you write, just so you all know. So no one will be judging what you see. And also you can't see someone else's answer, so you can't be like, oh, that's the answer. All right. So we'll see if this works or not. There's lots of interesting stuff here. So let's look at something like, let's look at something like this. Let's do the limit. And I'm really just looking at Burke's homework assignment because there's some good questions here. Well, that's actually, well, fine. Still worthwhile, even though this is kind of not exactly what you guys asked for. We're going to look at this one anyway. Limit as x approaches 1/4 from the right-hand side of the inverse cosine of the natural log of the 8th root of 4x. Seems kind of needlessly complicated. That's all right. Don't worry, we'll get to the limit soon in just a second. I saw this one and I thought, oh, it's kind of fun. What happens if we plug in 1/4? Well, we get a lot of garbage, but if we plug in 1/4, I'm going to get the inverse cosine of the natural log of the square of the 8th root of 1. The natural log of 1 is 0. And the inverse cosine of 0 is, it's not undefined. So whenever I think about inverse cosine or inverse trig function in general, the inverse trig function is always asking you for an angle. What's the angle that if you took cosine of that angle, you would get 0? And before you guys, so I want you guys to write down an answer. And in the chat, I'm asking you all as well. What's the inverse cosine of 0? I want to see lots of answers because how many of you are there? There's 15 of you, 14 of you. I want to see some answers. I see one answer so far. Okay. I guess, yeah, see some other, yeah, I'm seeing some right answers. Good. Although we would want to write it in radians, not in degrees. Love to see some more answers. I've gotten some, yeah. So there should only be one answer. All right, so inverse cosine is 0. I'm gonna, what do you guys think it is? Pi/2 is the one and only answer because cosine of pi/2 is equal to 0. Now I know some of you might be saying, hey James, well, yeah, it's true that cosine of pi/2 is 0, but so is a lot of other angles, right? It's also certainly true that cosine of 3pi/2 is 0, or cosine of -pi/2 is 0. But here's the important thing about inverse trig functions. They have a very specifically defined range. So when you talk about the inverse cosine, the only values you get for inverse cosine is 0 to pi. So if someone said, what's the inverse cosine of -1, the answer would be pi, because cosine of pi is equal to -1. And just to expand on this idea a little bit further, cosine's kind of the odd man out when it comes to inverse trig functions. Inverse sine is negative pi over 2 to pi over 2. So if somebody asked you, what's the inverse sine of 0? The answer would be 0, because sine of 0 is 0. And if someone said, what's the inverse sine of negative 1? The answer would be negative pi over 2. Even though there's lots of other angles where sine of that angle is equal to negative 1, negative pi over 2 is the one and only value we have defined inverse sine of negative 1 to equal. And I want to be extra specific here. 3 pi over 2 is not a correct answer. I know 3 pi over 2 and negative pi over 2 are coterminal, right? They have the same spot on the unit circle, but they're not the same number. Right? Negative pi over 2 is like negative 1.5-ish. 3 pi over 2 is a lot bigger than that, right? It's like 4.5-ish. So just be careful, right? We really mean one and only value. And the reason why is because we need these things to be functions. And functions have this very, very important property that if you input one thing, you get out one thing, not two things, not 5 things. So that's why we've got this here. So let me actually get to what people actually said they wanted to see about, which was some limits to infinity. Yeah, there's lots of good questions here. Sure. So I'm gonna just kind of go, it feels like I feel like I should just again mention, even though I know we've talked about it a little before. I like these green pens, but I want them to work because I like them. When you have a limit to infinity of a polynomial divided by another polynomial, 3 things happen, or I should say one of 3 things happens. You either get the leading coefficient divided by the leading coefficient, if the degrees are the same, right? If P and Q both have the same highest power. If the degree of P equals the degree of Q. And then you get 0 if the degree on top is less than the degree on the bottom. And you get some sort of infinity if the degree on top is larger than the degree on the bottom. And we'll see that play out here in a little bit. Let's look at some examples. Like, say I want to take the limit as x goes to infinity of 1 over 6 minus 5 over x to the 3rd. This doesn't seem too terrible. It looks like what's going to happen to 5 over x to the 3rd? Well, x is getting large, so that's going to get small. So we're going to get 1 over 6. Seems reasonable. Right. Goes to 0. And the same thing's going to be true. The limit as x goes to minus infinity. It's also going to be 1/6. The same sort of reason. Now, something you might see with this, which I think is maybe not the right way to go, but you might have started out with this being the limit as x goes to infinity of x cubed over 6x cubed minus 5. That's the same limit, just expressed differently. All I did to get from here to here was I multiplied the top and bottom by x to the 3rd. But really, what I really want to say is, usually you would start with something like this and then divide everything by x to the 3rd to get to something like that. And I should say, I don't know what your teacher is going to want you to show as far as work on a test. Some people might be like perfectly cool with you saying, oh, this is just 1/6. Some people might want you to first do this step and then say it's 1/6. I would, if I were a student, I would err on the side of showing more work than less work. That's always, almost always the right call in the math class. Let's look at the limit. X goes to infinity of 5 minus 6 over x over 6 plus square root of 8 over x to the 10th. These are some interesting questions on this homework assignment. I feel like this, to me, this seems like a not hard question to answer. I think everybody should be able to write. So I want everybody in the chat to write down the answer to this question. I think this one's pretty straightforward. Put it in the chat. There's a lot of you, and I only have 3 responses so far. So you're missing out on an option. Yeah, thank you. Good. All right. So again, right, when you have something divided by x and x is getting large, that thing's just going to go to 0. So you're getting 5 minus 0 over 6 plus 0, which is going to be, hey, 5, 6. Not a huge surprise there. Let's look at some more interesting questions. I mean, not that those aren't interesting, but let's change it up. Let's take the limit as theta goes to minus infinity of cosine of 3 theta over 9 theta. Now, if I were being not particularly observant, I might think this is one of those like wish things that I was talking about before, where we want like sine theta over theta. This is not that for 2 reasons. One, it's cosine and not sine, and they are very different when it comes to that. Right? Cosine theta over theta does not go to 1 as theta goes to 0. But the other point here is that theta is not going to 0. Theta is going to minus infinity. So I know I said a thing a while ago, maybe not that long ago, about when you see cosine or sine and you see minus and plus infinity, we should be thinking of using the something you like to eat theorem, the sandwich theorem. When you see a sine or a cosine and the limit to infinity, 99 times out of 100, it's probably a squeeze theorem question. And we're always going to start off a squeeze theorem or a sandwich theorem by saying we know that sine or cosine of whatever lives between what and what. Always, every time, for sure. And then our job is to make sure that the thing that's in the middle here looks like the thing we want to take the limit of. So I'm going to divide everything by 9 theta. Make sure it's 9 theta and not 90. And then there's a couple ways you can do this. I have actually become partial to writing it this way. I'm just going to take the limit of each piece. So it is true, it's a very true statement, that if a function is less than or equal to another function, its limit is less than or equal to the limit of the other function. The limit doesn't change the inequality. So, right, because what we're really saying, this is always less than or equal to that. So if this is always less than or equal to that, anything this approaches should always be less than or equal to anything that approaches. So the limit as theta goes to infinity of negative 1 over 9 theta is less than or equal to the limit as theta goes to infinity of cosine of 3 theta over 9 theta. It's a lot of writing though. Limit as theta goes to infinity of 1 over 9 theta. And then this is 0. So 0 less than or equal to the limit as theta goes to infinity of cosine of 3 theta over 9 theta, and that's less than or equal to 0. And if you're bigger than or equal to 0 and less than or equal to 0, you got to be 0. Yeah.
Why does infinity change from negative?
Oh, because I dropped, because I'm a dork and I missed the negative there. Yeah. Now I will point out, it would also be true if we were going to infinity. But you're right. The question was specifically negative infinity. I'm sorry about that. I just totally forgot that, to be honest. Yeah, it should be the limit negative infinity. But the same thing still happens, right? Whether theta is going to infinity or negative infinity, 1/9 theta is still an extremely small number, and negative 1/9 theta is still an extremely small number. That's an excellent question. Yeah. So all good questions. So it's hard to see the chat too. Maybe the problem is that I'm going to move this here so I can maybe make the chat more in my field of vision here. Yes, theta should go to negative infinity, which is gross. And why is it 0? Excellent question. So this is something that's going to come up a lot. Why is this limit as theta goes to minus infinity of, say, 1/9 theta? Why is that 0? Well, right. Well, I'm going to be a tiny bit more precise, but yes, you're right. I would say any finite number divided by infinity is definitely getting infinitesimally small. So again, I should say this never actually equals 0, right? If you graph 1/9 theta, it's going to get super duper close to 0, but it's not actually equal to 0. But that's not what the limit says, right? The limit doesn't say the function equals 0. The limit says if theta is big, then 1/9 theta is very close to 0. And that's why the limit as theta goes to negative infinity, or I should say if theta is big and negative in this particular case. So when I say something's big, I really mean it's positively big or negatively big. Right? Negative infinity, I'm still thinking of it as a big number. It's just big in that direction instead of that direction. Hopefully that addresses your question. So let's look at another example. Something like, yeah. I like these questions, and I'm really looking at a Burke's homework assignment here and just going through. I'm modifying them, although I imagine my questions are probably different than the ones you have on your assignment anyway, because it always gives you like slightly different questions. So, but they're good questions, and they're using all sorts of interesting variables. The limit as r goes to infinity. Oh, this is going to be a good one. Yeah, of r plus 2 sine of r over. Oh, this is going to be gnarly. 4r plus 5 minus 6 sine of r. Yeah, okay. So there's a couple ways to approach this, but there's definitely, I think in this particular one, a better way. So oftentimes I would start with something and try and make it look like this whole thing. That's not what I'm going to do here. We know this limit, or if we think about it for a minute, we probably know what this limit's going to equal. Are there any guesses in the chat or in live, peoples? 0 is a good guess, but it's not the right answer. So if we ignore the sign parts for a second, are the degrees the same or not? The degrees are the same, right? Both of us have a degree 1. And so I see some correct guesses in the chat. If the degrees are the same, we usually think about the limit as being the quotient of the leading coefficients, which would be what in this case? 1/4. And that is what the limit is. Now, in my opinion, and I imagine most professors' opinions, you do have to show some work here. If I was going to show this limit was equal to 1/4 usually, right? If I just had that, what would I divide everything by? R. That's what I'm going to do. So this is going to be equal to the limit as r goes to infinity of r over r plus 2 sine r over 4r over r. Now, I think it's silly to actually write all this out. I think it makes way more sense to simplify this in your first step. And instead of writing r over r and 4r over r, write the limit as r goes to infinity of 1 plus 2 times sine of r over 4 plus 5 over r minus 6 times sine of r over r. Okay. So I'm going to ask you a question, and it's a little precarious. What's the limit of sine of r over r? So it is precarious, and that is the right answer if r is approaching what? 0. It's definitely true. The limit as r goes to 0 of sine of r over r equals 1. For sure, yes. But what's r approaching? Infinity. And as r goes to infinity, that limit is definitely not equal to 1. So what's the limit as r goes to infinity of sine of r over r? It's going to be 0, but how do you show it's 0? So here's the thing. Here's the point I'm trying to get at. I know that we have the thing is we don't have a constant divided by something that's getting infinitely large. We have a sine function which is oscillating back and forth between -1 and 1. So typically what people usually require for a question like this is like, oh, this equals 0 by the squeeze theorem. We can say that sine of r is between 1 and -1, and then divide everything by r. Sine of r over r is between 1 over r and -1 over r. And it's totally true that, sorry, it's totally true that you can't see that. It's definitely true that the limit as r goes to infinity of 1 over r is 0, and the limit as r goes to infinity of -1 over r is 0. So usually when you see something like this, there's an expectation of using the squeeze theorem to show that these parts are in fact going to 0. On the other hand, there's no expectation of doing anything other than just saying this part's going to 0. So we do get 1/4. We get 1 plus 2 times 0 over 4 plus 0 minus 6 times 0, which is 1/4. But what I want to point out here is that when you have something like this and it looks kind of like a rational function, but you have some sines or cosines in either part, you can't just use the rule, even though it's true that you get the quotient of the leading coefficients. You have to kind of think about that, but then still use the squeeze theorem for the sine or the cosine part. Question?
Yeah. Whenever there is a fraction or sometimes sine r over r or pi over r, is that always going to turn into 0 because it is a fraction?
As well, I would say if you're taking the limit as r goes to infinity or minus infinity, then yes, that limit is going to be 0 because you have something that is finite on top divided by something that is getting infinite on the bottom. So yeah, that fraction is going to get closer and closer to 0 because of that.
Okay. Thank you.
You're welcome. Right. Okay. Look at. Sure. That's a good question. Yeah, and it's good. I feel like I'm like in the private chat here. I'm getting a lot of responses. It's good. Keep it up. Keep it up, Zoom. You guys are also doing a very good job. I'm not to discount you, just so I'm like this is new, so I feel like I should. It's good. Let's look at this. Let's look at both of these. The limit as x approaches, we're going to look at infinity and negative infinity of 2x to the 13th minus 3x to the 5th plus 7 over 6 plus x minus 7x to the 8th power. And no one should write a rational function this way. This is terrible. I should be kind, or we should rewrite as 2x to the 13th minus 3x to the 5th plus 7 over negative 7x to the 8th plus x plus 6. Now, I will point out, if you're in, I think, Jacob's class, I think he would, or at least the way the TA wrote solutions to a question like this, you would say, well, this is essentially the limit as x goes to infinity of what's the only thing that actually matters here. X to the 13th on top, and now I have a question. Do I care about the coefficients? Well, I don't care about their values. I do care about their signs. That -7 is important, not because it's 7, because it's negative. So I would encourage you to just include the coefficients on them, even though the actual numbers are not important. Because now this reduces to the limit as x goes to infinity of -2/7 times x to the what? Let's see, 13 minus 8 is 5. And as x goes to infinity, infinity to the 5th power is still positively infinitely large, but then it's multiplied by a negative. This is going to end up being negative infinity. If I were doing this the way I usually do it, I would write this as the limit as x goes to infinity. And I would divide everything by x to the 8th. So I would have 2x to the 5th minus 3 over x cubed plus 7 divided by x to the 8th over -7 plus 1 over x to the 7th plus 6 over x to the 8th. And all the things being divided by x to some power are going to go to 0. I mean, you don't really need to cover your mouth if you're coughing into your mask. Right? It feels kind of silly to do this, right? Anyway, so what am I going to get here? I'm going to get 2 times infinity divided by -7. That's going to be negative infinity. So depending on what this is the way I would always do it, but your teacher might want to use something else. So like if this is kind of the work they're looking for, that's also totally fine. It is true that in these rational expressions, the dominant terms are the only things that matter, right? In the numerator, the only thing that actually matters is the highest power of x. In the denominator, the only thing that matters is the highest power of x. But the coefficients also do matter, right? Or at least the signs of the coefficients really do matter. What if instead we were doing the limit as x goes to -infinity of this same thing? Well, I can still do the same work, right? It feels kind of silly to write it out again, but we could say it's going to be the limit as x goes to -infinity of 2x to the 5th minus 3 over x cubed plus 7 over x to the 8th over all this other stuff. Yes, of course, yeah. Always, please don't hesitate to let me know. So now, as x goes to -infinity, what are we going to get? Well, what am I going to get on top? Positive infinity or negative infinity on top? Negative, because it's a negative raised to an odd power, which is still negative. So I'm going to get a negative infinity on top, and I'm going to try and say actual words and not just the. I'm going to get a -7 on the bottom. Negative divided by negative is positive. So, as I said before, but I'll repeat right here, when the degree on top is larger than the degree on the bottom, we get some sort of infinity. And your job really is to just figure out what the sign is. Is it positive? Is it negative? And it depends on two things. It depends on what the coefficients are doing sign-wise, and also what your infinity raised to a power is also doing. Because if it's a negative infinity raised to an odd power, that's going to also get a negative attached to it. Or in this one, you also could have done this thing. It said, oh, well, it looks like I've got -2/7 times x to the 5th. And then since x is going to negative infinity, I get -2/7 times a negative large number, and that's a positive large number. Ooh. Interesting. Yeah. What time is it? Okay, we got plenty of time. Got lots of time. So here's what I want you all to try for yourselves. Sure, yeah. The limit as x goes to infinity of, I'm going to write this in a slightly more suggestive way. Not like that. 1 over x cubed plus 1 over x to the 8th over 1 over x to the 6th minus 1 over x to the 8th. And before you get going on this, I'm just going to ask you, if you quote unquote plugged in infinity, what would you get? 0 over 0, which we know is indeterminate, which means indeterminate is just a fancy word for, I mean, okay, really it's a fancy word for, it can be anything. But really, when you think of the word indeterminate, you should be like, that's a fancy word for, I have to do more work. That's what indeterminate really means. I have to do more work. So, yeah, I would try something. So I know it's kind of a weird question, but how do I answer this question? No, it's still the right question. I guess it might be helpful to see it this way. So here's the question I want to ask you all. What's the highest power of x? -3. That's the highest power of x. I might consider dividing everything by x to the -3rd. But if you divide by x to the -3rd, you're really just multiplying by, I hate the days. You really just multiply by x to the 3rd. I would try multiplying everything by x to the 3rd. Try it. See what happens. I would do it using this particular version. See what happens if you multiply each of those terms by x to the 3rd. Ooh, actually, you know what? You could try that. It's going to be problematic though. So remember the other thing I said? Maybe. So I asked the wrong. Well, I didn't ask the fully right question. I asked for the highest power of x, but I actually should have asked for the highest power of x in the denominator, right? It has to, so let me just point out. Here's what's going to happen if you multiply by everything by x to the 3rd. You're going to get 1 on top, 1 over x to the 5th, 1 over x to the 3rd, 1 over x to the 5th, and these are still both going to be 0, which is going to be a problem. So you don't want to divide everything by x to the 3rd, sorry, x to the -3rd. You want to divide everything by x to the highest power in the denominator. So what's kind of cool about this is the thing we're trying to do still actually works, even if the powers are wonky. We're still just using the same idea, right? We've got powers of x in the numerator and the denominator, and we're just, again, dividing everything by the highest power of x in the denominator. It just happens to be a negative number. Give it a try, see what you get. For those of you in the chat, when you get an answer, type it in there. I want to see your answers. Yeah, there's some good. Okay. It might be infinity. I'm not actually sure. It might not. It could be, but it could be something else. Actually, I suppose we could have a guess at the answer before we even do the work. But I'm not going to say what that is yet. Yeah, I didn't. I'm going to ask you a question. So I should back up. It's not a rational function. Rational functions are specifically polynomials over binomials. Binomial doesn't have negative powers. Not a rational function. But what I want to mention here is that even though it's not a rational function, we can still apply some of the same logic. Okay, so even though it doesn't actually make sense to talk about degree, I'm just going to ask, what has the highest higher power? The numerator or the denominator? The The numerator has the highest power. It's -3. And so when the numerator has the highest power, we've seen in the past that the overall limit is some sort of infinity because the top is getting bigger faster than the bottom. Or in this case, I guess smaller or less fast. So I think the answer is infinity, but let's find out. If I distribute the x to the 6th here, I get the limit as x goes to infinity of x cubed plus 1 over x squared over 1 minus 1 over x squared. And yeah, that's looking a lot like it's going to go to infinity plus 0 over 1 minus 0, which, hey, oh yeah, that's infinity for sure. Yep, I think the limit's infinity too. As well, sorry. I'm a little too zoomed in. All right, a couple more limits to infinity. Then we might take a little break. So I can use the bathroom. Water. Was there one of those? I don't see one of those. Let me take a look quick. Oh, that's too bad. That's definitely worth looking at. Yeah, we should do. Well, actually, okay. Sorry, I'm just having this conversation with myself over here. Maybe I should include you guys too. Let's look at this example. So the limit as x goes to infinity of the square root of x plus 9 minus the square root of x plus 25. So this is another, oh, why are we, sorry, someone has a question. Why are we unable to multiply by x cubed? So that's an excellent question. Let me go back for just a second. So if we multiply by x cubed, here's what we get. Limit as x goes to infinity of 1 plus 1 over x to the 5th over 1 over x cubed minus 1 over x to the 5th. And the issue here is that while the top is going to 1, totally fine, the denominator is getting closer and closer to 0. And the issue here is that it's often hard to determine if that's a slightly negative number or a slightly positive number. So is this slightly positive or slightly negative? Because that's the real determining factor. If the denominator is slightly positive, it's going to positive infinity. If the denominator is slightly negative, it's going to negative infinity. And it's not that you can't make this work, but it's definitely easier to make it work this way. So that's what's going on there. Here, if you really did some work, you could factor out a 1 over x cubed and have a 1 over x cubed times 1 minus 1 over x squared. And then you could see that the denominator as x goes to positive infinity is slightly positive. But again, that's more work than I want to do. I would much rather do it the easier way. This can work. It totally could work to multiply by x cubed. It's just more work to do that. I'm all about doing the least amount of work we can to get there efficiently. So here we have what's typically called an infinity minus infinity indeterminate form. What's infinity minus infinity? I don't know. Indeterminate. It's not clear until we do more work. So in this case, the work we're going to do is we're going to multiply by a conjugate, which is 9 times out of 10 what we do when we see a square root minus something else or something minus the square root. So we're going to multiply this by really we're going to multiply by 1. So I think we're actually allowed to multiply by the square root of x plus 9 plus the square root of x plus 25 over the same darn thing. And what are we going to get? Well, we got the square root of x plus 9 plus the square root of x plus 25 in the denominator. And in the numerator, we're going to have, let's see, x plus 9 times x plus square root of x plus 9 times square root of x plus 9 is x plus 9. The middle terms cancel. That's why we multiply by the conjugate. And we're going to get a minus the square root of x plus 25 times the square root of x plus 25, which is just x plus 25. Right? And just to be super duper clear, we're foiling out the top. That times that is x plus 9. That times that is the opposite of that times that, and so they cancel out. I just don't want to write it all. Like I will write it out if you guys want me to, just say the word. but if you don't need me to, I'm not going to. But that's always the case, right? Whenever you multiply by a conjugate, a minus b times a plus b, it's always the first thing squared minus the second thing squared, and the middle terms cancel. Why we do it. So simplifying this a little bit, you get the limit as x goes to infinity of the x's cancel on top. I get negative 16 over a denominator which is getting larger and larger and larger. So this limit is going to be 0 because the denominator is super large and the numerator is finite. So in this particular case, in this indeterminate form, this infinity minus infinity happens to be 0. But I'm going to stress with this next example, the limit as x goes to, sorry, I should say, infinity minus infinity can be anything. It's interesting. So I should point out that in this particular homework assignment from Burke, this question also asks for the limit as x approaches minus infinity of the same thing. Now, the answer here that I'm sure is what the right answer is it doesn't exist. But that's not even a really good thing to say, because really the right answer should be, it doesn't even make sense, right? You can't take the limit as x goes to negative infinity of x plus 9 because you can't plug in very large negative numbers into a square root and get anything real out. So this limit doesn't even make sense. But if I had to give an answer, I would say it doesn't exist. The way I got negative 16 on the top is because I've got x plus 9 minus x plus 25. And so that's going to end up being x plus 9 minus x minus 25. And then the x's cancel, and 9 minus 25 is negative 16. And yes, the other person, yeah, exactly. It would be an imaginary number if we had x being too negative. And we don't deal, right, when we're talking about limits or functions or anything, we're always talking about real valued functions, meaning when you input something in the domain, you're supposed to get a real number out. There is a lot of math that deals with functions that give you imaginary numbers as the output. That's not what we're here about. Not that it's not something that isn't something people can look at, it's just not what we are dealing with. All right, let's look at a similar but very different question. So let's look at the limit as x goes to infinity of, I don't like that one. Let's do this one. Square root of x squared plus 10x minus x. And actually, before we do that one, so I'll again point out, before we do this one, it's definitely an indeterminate form. It's an infinity minus infinity, no doubt. But before we do that, let's ask the other question. What's the limit as x goes to minus infinity of the square root of x squared plus 10x minus x? Oops, let's actually see the question maybe. So I should ask you all, as x goes to negative infinity, what's happening to x squared plus 10x? Is it getting large? Is it getting negatively large? Well, what's the dominant term? X squared, right? It's definitely dominating 10x. And as x goes to negative infinity, x squared would go to positive infinity. Now, you might say something like, well, hey, you just talked about, James, how infinity minus infinity is indeterminate form. And technically, you have infinity minus infinity here. Because x is going to negative infinity, x squared is infinity, plus 10 times negative infinity, right? That's infinity minus infinity. So you could say, well, you're kind of being a little hand wavy there. And I'd say, well, okay, fine. But it is true that x squared does dominate 10x, right? If x was like negative 1,000, that's going to be 1,000,000 minus 10,000. 1,000,000 is way bigger than 10,000. But if you really don't like that, you can do the following. Say, just factor out an x. Then it's very clear that as x goes to negative infinity, you have a negative big number times another negative big number, which is going to be a positive big number. Okay, but then look at this. So you're getting the square root of a very large number, which is a very large number, minus a very large negative number. What's that limit going to be? What's infinity minus negative infinity? Double infinity? It's infinity. So I just want to point out, infinity minus infinity, definitely indeterminate, have to do more work. Infinity plus infinity is just infinity. Or in other words, infinity minus negative infinity is just infinity. So when you've got these square root things going on, if you're looking at like both limits, usually one of them is kind of nice and one of them kind of has more work to do. So let's take a look at this one here. I'm going to do the same thing I did before. I'm going to multiply by the conjugate. So I'm going to take the square root of x squared plus 10x minus x and multiply it by the square root of x squared plus 10x plus x over the same thing. And then we multiply it out. The top is going to be, well, the bottom is going to be easy. And the top is going to be, well, we FOIL it out. We get this times this, which is x squared plus 10x, minus x times x, which is x squared. Interesting. Yeah. Sorry, I'm just thinking about something here. Anyway, so if we simplify this, the x squareds cancel, and we get the limit as x goes to infinity of 10x over the square root of x squared plus 10x. And now I'd like to talk about how this is an infinity over infinity, right? The numerator is definitely going to infinity. The denominator is definitely going to infinity. And even though it's not a rational function, actually I've got a square root on the bottom, what's the highest power of x in the numerator? Right, x to the first. And even though it's not really a good question, what can you kind of think of as the highest power of x in the denominator? Well, it's not x squared. It's the square root of x squared, which is x to the first. So I know we don't actually have that. But what we often think about is, well, essentially, I'm going to pretend like it's just, I don't care about this less dominant term, right? This 10x doesn't really matter. And the square root of x squared is kind of like x. So what I really am seeing here, even though it's, even though it's not exactly 100% true, is the degree on top is 1 and the degree on the bottom is also 1. I have the same degree on top and bottom, which means I'm probably going to get some non-zero number. Now, the way we show the work here is a little bit annoying, not going to lie. It's kind of a pain in the butt. What we usually do is from inside the square root, we factor out an x squared. So I'm going to write this as 10x over the square root of x squared times 1 plus 10 over x. And now, this is the question we're going to revisit in a second here. What's the square root of x squared? Absolute value of x. Thank you very much. That is the exactly right answer to the question that I was hoping someone would say. But x is positive. So I see, so I just want to make sure, is everyone cool with this? Would anyone like me to talk more about why this is the opposite value of x? Yes, for sure, 100%. So why is the opposite value of x? Well, the square root of x squared equals the opposite value of x. Here's the way I like to describe it. What's the square root of 5 squared? See, 5 squared is 25. Square root of 25 is 5. But what's the square root of negative 5 squared? See, negative 5 squared is still 25, and the square root of 25 is positive 5. So the square root does the same thing that the opposite value function does, right? It takes a positive number and just spits it back at you. It takes a negative number and gives you back the corresponding positive number. That's the absolute value. So the square root of x squared literally is the same exact function as the absolute value of x. And so if x is a positive number, which it definitely is, then the absolute value of x is just x. Right? If you're taking the absolute value of 5, you just get 5. And we know x is positive because x is going to infinity. It's about as positive as you can get. So this all boils down to saying, well, this is going to end up being the limit as x goes to infinity of, let's see the things maybe, 10x over x times the square root of 1 plus 10 over x plus x. But now we can divide everything by x or factor out x, whatever you want to call it. If I divide everything by x, 10x divided by x is 10. X times the square root of 1 plus 10 over x is just the square root of 1 plus 10 over x. And x divided by x is 1. And let's see what happens as x goes to infinity. 10 over x goes to 0. And you're left with 10 over 1 plus 1. Exactly. So in this particular example, infinity minus infinity is 5. This first infinity is 5 bigger. Oh, sorry, you can't say 5.2. The first infinity is 5 bigger than, I mean, it's not really like we don't actually say that, but it's kind of funny to talk about that way. Now, this isn't a good example of what I wanted to say, though. That one doesn't make sense to talk about. Yeah, yeah. Uh-huh. Right. So I maybe skipped this, or didn't skip a step. I didn't write. So a step you could have written in, wanted to, was you could have rewritten this as, I'm just going to write the fraction without the limit because I don't have a lot of space. You could have written that as 10x over the square root of x squared times the square root of 1 plus 10 over x plus x. That's the step I'm skipping there. So you can add the 1 inside the square root with the 1 in the denominator. Well, I'm not, so no. What I'm doing there is I'm taking the square root of 1 because the square root of 1 is what? 1, right? The square root of 1 is 1. So again, I'm not showing all the steps. What I'm really just saying is like the square root of 1 plus 0 is the square root of 1, which is 1. And then 1 plus 1 is 2, 10 over 2 is 5. All right, let's look at one more question in this vein. And then we'll take a little break. And then then we can either continue talking about limits to infinity if you want to, or we can start talking about the limit definition of the derivative and tangent line, stuff like that. So let's talk about the limit as x goes to negative infinity of, I don't want to do that. Oh, I could be smart about it if I was, that's a good question. I like it. Okay, let's do this. Let's do the square root of x squared plus, let's have some fun, 12x plus x. All right. This looks wild. You guys are like, what's he talking about? So why do I think this is wild? Well, because it's still indeterminate. It just maybe doesn't have the usual kind of look. Is this an infinity minus infinity? Yeah, it is. Because the square root of negative infinity squared plus 12 times negative infinity, that inside is going to positive infinity. It'd be problematic if it wasn't. Right? We can't take the square root of negative numbers. So if if the inside was going to negative infinity, we'd have a huge problem. But that's definitely going to positive infinity. And then you're adding a negative infinity. Oh yeah, that's certainly a infinity minus infinity or plus negative infinity. Indeterminate. Do more. I think this limit's going to be -6. I'm not 100% sure. It's okay. We're going to do the work. The work is very much the same as what we just did. In fact, I kind of feel like I should let you guys work on it. I'm going to let you work on it a little bit. So I'm going to put the previous work back up so you can see it again, even though I imagine many of you wrote it down. And I'm going to start you off with the first step, which is you're going to multiply by the conjugate. Oh, this pen's starting to die. Okay. Good thing I got a lot of them. That is a 12x, yes. Sorry if it doesn't look like a 12. So there's your first step. But the work's going to be very, very similar to what we did before. So work on that for a bit. I'm going to go use the restroom, grab some water. You all are you're always welcome to use the restroom whenever you want. So you can go back later, never go, totally fine. I'll be back shortly. So I will mention the opposite value thing is going to give us a slightly different piece this time. Let's take a look. Then grab the wrong. Yeah, right, exactly. So that's kind of the crux of this particular type of problem, is that the absolute value, if you're going to infinity, is positive x, and if you're going to negative infinity, it has to be negative x to turn it into a positive number. So I'm going to write this as the limit. X is minus infinity. We're going to multiply at the top. We're going to get x squared plus 12x minus x squared over this. And let's go ahead and factor out x squared from the square root. So we're going to get x squared times 1 plus 12 over x minus x. And then the x squareds cancel in the numerator. And in the denominator, that's the square root of x squared times the square root of 1 plus 12 over x. That's x. And then in this case, the square root of x squared being the absolute value of x has to be negative x, because x is going to negative infinity. This is going to be the limit as x goes to minus infinity of 12x over negative x times the square root of 1 plus 12 over x minus x. And then we can divide everything by x and get the limit as x goes to minus infinity of 12 over negative square root of 1 plus 12 over x minus 1. That's a negative out there. And then finally, plugging in negative infinity, we get 12 over negative square root of 1 plus 0 minus 1, which is 12 over negative 1 minus 1, which is negative 6. Now, I want to point out, sometimes people ask a follow-up question very poorly. Someone might ask you, well, James, what if the limit was going to positive infinity? And depending on the way the question started out, different things can happen. If you were not being careful, you said, what's the limit to positive infinity? Well, you thought, well, actually, that's not true. You'd be perfect. You would still get the same sort of, yeah, never mind. My question's back. If we did ask the question, what's the limit as x goes to positive infinity? We should look back at the original expression. Be like, oh, well, if x is going to infinity, I've got infinity plus infinity, which is infinity. Yeah. All right. One last kind of thing here, just to see. Here's one more example that we're not really going to work through. I just want to point out something. Let's say our function was this. It's sure. Let's say it's the. Now I'm trying to make something up that doesn't seem too bonkers. 3x over the square root of x squared plus 10x. Is that what I really want? Sure, that's not that interesting, but it's fine. You can use limits. Yeah, exactly. Yes, if x is going to infinity in the previous problem, the limit would be infinity. Here, you can show that f of x has two different, I don't think I need to write that, horizontal asymptotes. And I'll even tell you what they're going to be. They're going to be y equals 3 and y equals negative 3. If you look at the limit to the right, as x goes to positive infinity, well, I think you guys can see what's going to happen. We're going to bring out the x squared. It's going to turn into the square root of x squared is going to be x because x is positive. And we're going to get the limit as x goes to infinity of 3x over the square root x squared times 1 plus 10 over x. And then that's going to be the limit as x goes to infinity of 3x over the absolute value of x times the square root of 1 plus 10 over x. But the absolute value of x in this case is just x. And so that's going to cancel with the x there. And so then we end up getting 3 over the square root of 1 plus 0, which is just 3. In the other direction, the limit as x goes to minus infinity of the same thing would be the limit as x goes to minus infinity of 3x over the absolute value of x, 10 to the square root of 1 plus 10 over x. So now in this case, the absolute value of x is a negative x. So we end up getting the limit as x goes to negative infinity of 3x over negative x times the square root of 1 plus 10 over x. The x's still cancel, but now you're left with the limit as x goes to minus infinity of 3 over negative square root of 1 plus 10 over x. And if x goes to infinity, that's going to be 3 over negative square root of 1 plus 0, which is negative 3. So this is an example, and this is kind of a typical example of a function that has two horizontal asymptotes instead of just one. That's the most you can have, by the way. You can only have two horizontal asymptotes, one to the right and one to the left. Most of the time they're the same. Sometimes they're different. Sometimes you just have one on one direction and nothing in the other direction. But two is the most you can ever have. All right. And as far as I'm concerned, I think I've said enough about limits to infinity, unless you disagree and you have questions you would like to ask. Fine to disagree. All right. So let's go ahead and start moving in the direction of talking about derivatives and what derivatives are really all about. Oh, sorry, there's a question here. So someone asked a good question here. By looking at the equation, is there a way you can tell we'll have a horizontal asymptote like you can tell for a slant asymptote? So you can tell typically a function will have a horizontal asymptote if the highest power of x on top is less than or equal to the highest power of x on the bottom. I'm not saying degree, right? Because it's true even if they're not rational functions. So I know right off the bat that something like this, f of x equal to 2x cubed plus 5x plus the cube root of x over negative 4x cubed plus x squared plus the square root of x plus 1. I know this is going to have a horizontal asymptote of negative 1/2. At least it is going to have it to the right. To the left, it's not going to have one because x can't be super negative because of the square root there. But we definitely have a horizontal asymptote because I'm looking at the highest powers and looking at their leading coefficients and dividing them. And it's true that if the highest power on top is less than or equal to the highest power on the bottom, you're going to have a horizontal asymptote. If they're equal, you take this quotient. If it's less, you get 0. So if you had something else like g of x equal to something bizarre like, sure, let's make it really fun. Let's say we had something like 2x to the 5/3 plus 4x minus sine of x over 3x squared plus 6 cosine of x. Well, even though I know I've said things about sine and cosine, as far as horizontal asymptotes are concerned, you should kind of just ignore them. And we would use, if we were really trying to show that this one had a horizontal asymptote of 0, we would show all the work and do all the ridiculous squeeze theorem stuff. But here I can just say, well, look, I can see that my highest power on top is less than my highest power on the bottom. So this limit as x goes to infinity or negative infinity of this expression, 2x to the 5/3 plus 4x minus sine of x over 3x squared plus 6 cosine of x is definitely going to be 0. Because the bottom thing's going to be bigger faster than the top thing. Right, so excellent. So someone just said, when I graphed the last function, this one here, I saw that the graph does not go in the negative direction, right? Because here, the domain, there might be some other issues, but certainly x has to be bigger than or equal to -1. You might have some other things you have to also observe, but for sure, we at least have this being true. So we don't get it one to the, oh, you mean the last. Oh yeah, you're, so zoom out. Are you talking about this one? Zoom out a little bit. Because what's happening with this one is that this one isn't defined for x between like 0 and -10. Right? If you actually, so if you look at this, right, you have to have x squared plus 10x greater than or equal to 0. Actually, just strictly greater than 0, which means x times x plus 10 has to be greater than 0. So x has to be greater than 0 or less than -10. But between 0 and -10, it's not defined. But it's good. So that's actually a really good point. In fact, let me show everybody because I think that's worthwhile. So when you're using Desmos or any graphing tool, you have to like be aware that sometimes you're not getting the whole picture. So just so everyone can see what we're talking about. If we graph that previous one, 3x over the square root of x squared plus 10x, right? It doesn't look like you got everything. Now, it definitely does have a horizontal asymptote at 3, right? Check it out. Get closer and closer and closer and closer to 3. Cool, cool, cool. Yeah, okay, looks reasonable. But someone's like, well, James, you said y equals -3 was also a horizontal asymptote, and it is, but we have to zoom out to see it. Oh, there's the rest of the function, but definitely not defined between -10 and 0. So good thing to be asking about and to be aware of there. Yeah, good question. I like that question. Thank you. Can I not just do the thing? Be easy. There we go. Good. Okay. Yeah, typically, if you've got things where you've got powers of x, if the degree in the numerator is less than the degree in the denominator, you're going to get 0 as your limit. Now, good question. Back to the, so let me address this first. The way you would show this, if you really wanted to show it, would be to divide everything by x squared, which is, again, kind of not fun. But if you do it, right, you get, okay, 2x to the 5/3 divided by x squared is 2x to the 1/3, 4 over x, sine x over x squared, divided by 3 plus 6 cosine x over x squared. This is 0 because we know it is. I made a mistake here. That's x to the -1/3 or 1 over x to, let's just do that. It's 2 over x to the 1/3. X is divided by x squared. This we know goes to 0 by the squeeze theorem. So does this. We would probably actually need to show it. And then we're going to get 0 plus 0 plus 0 over 3. Someone asked, it seems like the one we just graphed also has a vertical asymptote. How can we tell? Good question. Definitely looks like there's a vertical asymptote at -10. I think, right? Is that what it looks like? Seems reasonable. So that's a really good question. I think this bears, so we're almost, we'll talk about limit definition in just a second, but I do think it bears looking at. Oh my God, come on. Too many things. So in fact, I want to point out even more. Well, no, I'll just. So we are looking at this function. And I would like to know, where are the vertical asymptotes? So typically, how do we find vertical asymptotes for a function? We see where the, well, yeah, you're not wrong. Specifically, with one small exception, you're usually looking to see where the denominator of your expression is 0. Now, there is one exception to that. You also have to look where you might be taking a natural log of 0. Right? Natural log. So every other vertical asymptote comes from dividing by 0. But you also have a vertical asymptote when you have a logarithm of 0. So that's the kind of one extra exception for vertical asymptotes. So now we have to be super extra kind of careful here. I'm going to look for where does this denominator equal 0. Let's square both sides. I can factor out an x. So it looks like I'm getting x equal to 0 and x equal to -10. Oh, sorry, yeah. Do I have a vertical asymptote at both 0 and -10? The graph certainly didn't seem to indicate that. Definitely at -10, check. Sorry, I know you can't see it here. But 0 seems dicier. Well, here's the thing. You for sure get a vertical asymptote when you either take the log of 0, which I know is not what we're doing here, but I feel compelled to mention, when we have log of 0, or when we have a non-zero number divided by 0. And the problem with 0 in this particular example is when you plug in 0 for x, you're getting 0 over 0. So that's what's happening there. That's why it's not going to be. And I think if to answer the follow-up question that I imagine someone would ask, okay, James, well then what is the limit as x goes to 0 from the right of this thing? I think the answer is I don't know. I want to say, no, I think it's going to be a problem. Oh no, let's find out. We don't know until we try. So I'm going to try and do what we usually do when we have a 0 over 0 type. I'm going to try and cancel out the thing that's a problem. The x is a problem. We know that we can do this whole thing. It's the limit is x. I really hate writing this all again, but I'm going to cut to the chase. I know I have an absolute value of x, square root of 1 plus 10 over x in the bottom. Two questions. Question 1, how do I know I'm approaching 0 from the right and not from the left? Like, why would I make that choice? Well, the reason I'm making that choice is because I saw the graph. And I know the function's not defined between 0 and 10, -10, right? So this function, the domain is -infinity to -10 union 0 to infinity. It's not defined for x strictly just right less than 0. So it doesn't make sense to approach 0 from the left. And also I saw the graph, right? If you look at the graph, like, oh yeah, we're definitely approaching 0 from the right to see what that limit is there. It looks like it's going to be 0. I mean, maybe, if we zoom in a little, it's looking pretty 0-y. Yeah, I mean, I would venture to guess it's probably 0. It's undefined at 0 though. 19, whoa, yeah, undefined. Okay. So since x is positive, right? It is positive. We could say the opposite value of x is just x. So then we're going to get this. The x's cancel, and we're left with this. The limit as x goes to 0 from the right of 3 over the square root of 1 plus 10 over x. Okay, so now we're just going to talk it out. X is going to 0, slightly positive to 0. 10 over x is doing what? Is it getting big or is it getting small? I think specifically just 10 over x, right? So I would agree the whole fraction is getting small. But if I'm just talking about the part of circled in green, is 10 over x getting big or getting small? It's getting really, really, really big because I'm dividing by 0, and 10 divided by 0 is gigantic. So this is big, which means 1 plus it is also big, and the square root of it is also big. So we have 3 divided by a really big number, which is really small. That's a 0, by the way, not a 6. In case you're curious. So our fraction overall has a very large denominator, right? Our overall fraction has a very large denominator, which means the overall thing is small. So 3 is being divided by infinity. Exactly, yes. So yeah, to find, so broadly, to find vertical asymptotes, you find the places where the denominator is 0 and the numerator isn't. And then I suppose what I should really say in addition to that is the places where you have 0 over 0, you have to just check. Because a 0 over 0 could give you a vertical asymptote or it could not. So it's 0 over 0 is always a problem. Non-0 over 0, vertical asymptote, always. Always, yeah, always. The domain of this is everything from -10 to -10, union 0 to infinity. So we don't get everything from between -10 and 0 inclusive of those numbers. The range, I would just look at the graph. The range would be, that's an interesting, actually, so if someone gave you this graph, saying the range is a good question. The range here, just looking at the graph, how smart is that? Look at that. You can see both. The range is everything from -infinity up to where? -3. I don't get -3, but then I do get everything from where? What's the next height? What's the next lowest value I get after -3? 0. Do I get 0? No, but I get everything close to 0. And 0 up to +3. That would be the range of this function. I don't actually get 0. I don't actually get 3 or -3, but I get any number that is close to those numbers. Okay. All right. Good questions. Gosh, mouse, come back. Okay, there you go. All right, so let's go ahead and, for the last 20 minutes here, start talking about the limit definition of the derivative, or just derivatives in general. So, derivatives. And what I really want to say before we get going is just that a derivative, although a lot of people are going to say it's the slope of the tangent line, which is certainly one correct interpretation. When you think of a derivative, what I really want you to think of is it's a rate of change. It's how one thing is changing as another thing is changing. So the reason we often think of it as the slope of the tangent line is because the slope of the tangent line is showing us how y is changing as x is changing. But I can't emphasize it enough. You don't want to get stuck in the mindset of always thinking it's just this one particular thing, because it's really just a rate of change. It might be the slope when we talk about how y changes as x changes, but it might also be the velocity when we talk about how position changes as time changes. But again, to be very, very specific, or very, very general, I guess, really, a rate of change, if that's what derivatives are, and it's just how one thing changes as another thing changes. So slope of a tangent line is a good example. Right, we're saying that's really talking about how y changes as x changes. And it's always how the dependent variable changes as the independent variable changes. So usually being told, we know x is changing in this way, usually just increasing. How is y changing? Or another typical example is velocity. How position changes as time changes. Now, the thing about these other examples, velocity, is you can totally make that into a slope of a tangent line, because you can graph position versus time and then say, oh, the velocity is the slope of the tangent line. So it all, a lot of the time comes back to slopes of tangent lines, just thinking about slopes in general, but it's really more generally a rate of change. So to that end, we want to find the average rate of change, which we're going to abbreviate because writing out average rate of change 10 times is terrible. Let's just call it the of this function, f of x equal to x squared plus 6x on the interval from 1 to 3. So I left myself not quite enough room to graph it there. Instead. So let's graph this function. X squared plus 6x looks, sure. Don't really need the whole thing, but I know it has intercepts at 0 and -6. Something like that. Yeah, I don't love that picture though. So I'm gonna, even though that's the picture I drew, I'm gonna make it easier to actually see what I want to see. So here's the part I really care about. Let's just say we know it's doing something like this. Yeah, I still feel like my picture kind of sucks. My picture, I don't love my picture, but it's fine. It'll do. So here's the point 0. Oh, sorry, not 0, 0. Well, there is the point 0, 0. So let's find some values. This point here is 1. Well, actually, we're not going to find the values just yet. There's 1 comma f of 1. There's 3 comma f of 3. And if I want to find the average rate of change, I'm just trying to say how much increase do I get as x increases from 1 to 3? Or in other words, what's the change in y over the change in x? Or in other words, I know there's a lot of in other words here. That's because there's a lot of ways to think about this. What's the slope of the secant line? Secant line is the line that goes through 2 specific points on the curve. Well, we know how to calculate the change in y over the change in x. It's just literally the oh, that should be an f of 3, not an f of x. Sorry. It's the difference in the x's. Sorry, the difference in the y's divided by the difference in the x's. Totally. Yes, that's exactly what we have to do. So our function was f of x is x squared plus 6x. F of 3 is what? 9 plus 18. F of 1 is 1 plus 6. Yes. So to actually calculate this, we're going to say, okay, well, that's going to be 27 minus 7 over 3 minus 1, which is 10 over 2. Sorry, 20 over 2, which is 10. So the average rate of change of this function on that interval is 10, meaning for each increase of x by 1, y increases by 10. Sorry, my words look especially sloppily written there. Right, that's all the slope means. If x increases by 1, y increases by whatever the slope is. Yeah.
So what's the relevancy of having every line plus 8
So I was trying to calculate specifically the rate, the average rate of change between x equals 1 and x equals 3. And so to do that, I was finding the change in y, which is the difference in the y value at 3 minus the difference in the y value at 1. So what I've got here, f of 1 is 7. What I've got here is f of 3 is 27. And so what I'm doing is I'm saying, oh, well, my rate of change is just the difference in the y's, 20, over the difference in the x's, which is 10. I'm going over 2, I'm going up 10. That's my slope. Sorry, over 2, up 20. I keep saying 10 because the result is 10. Over 2, up 20, which has a slope of 10. So now we're going to ask the question, similar question for the same function. What's the average rate of change on a smaller interval? From 1 to 2. But we could draw the picture again. I don't think it's super necessary, especially because I feel like my picture is trash, but you know, I'll make the picture look a little nicer. It's still the same idea. We're still just finding the slope of this secant line. Oh, come on, James. You can pretend that that's the secant line if you want. The problem with drawing the secant lines is sometimes you actually draw them on the curve, even though they're right. It's not supposed to act. Here's a nice picture someone else drew. There's my secant line. There we go. And we calculate this the same way. It's still going to be f of 2 minus f of 1 over 2 minus 1. And that's going to be, let's see, f of 2 is going to be 4 plus 12. And f of 1 is going to be 1 plus 6. So I get 16 minus 7, which is 9 over 1. So the slope of that secant line is 9. A little bit less steep. Okay, how much time have I got? Okay. And the idea here is that we're going to keep asking this question. We're going to let that interval get smaller and smaller and smaller. So what about the average rate of change for the same function, which I'm going to try not to draw like garbage? What about the average rate of change of this function on the interval from 1 to 3 halves? Okay, things are starting to tighten up here. So now we're looking at this interval where it is just slightly above it, but it's hard to see. Yeah, okay. We should pretend like that goes through. Right. Sometimes my drawing skills could be a little bit better, right? Because that doesn't look like a very straight line. But the point is, the line, the secant part there is above the curve. If we calculate it, f of 3 halves minus f of 1 over 3 halves minus 1 is going to be, let's see, f of 3 halves, we're going to plug that into x squared plus 6x, yeah. Minus, we know that f of 1 is going to be 7 over 1/2. So that looks kind of gross. But if we calculate this, we get 9/4. 6 times 3 halves is going to be 9 minus 7. So let's see, that's 9/4 plus 2 divided by 1/2. I could get a common denominator here, but why don't I just multiply the top and bottom by 2 instead? It's 9/4 plus 2 times 2, which is going to be 9 over 2 plus 4, which is going to be 8.5. So here's what I want you to observe. The slope of this secant line, in fact, I'm super smart here. Maybe, and we can see, we'll see how smart I can be on short notice here. So here's the function we're looking at. Oops. And here's what we've found so far. We've got, yeah, we can do this, sure. We've got, this was our first secant line between those 2 points, and it's going to be y equal to 10x. Ah, come on, brain. Sorry. Sure. I'm like, I can almost do it fast, but not quite that fast. Nope. Yeah, I'm like, oh, come on. Sorry, 1 second. I really do want to show this to you, and I think it's kind of worthwhile, but I need to look at one thing really quick. Sorry. There we go. Y minus 7 equals my slope times x minus 1. Sure, so it should actually be y equal to 10x minus 10 plus 7, which would be minus 3. And that is not very easy to see anything that's happening there, right? Okay, it's kind of like, okay, there's the point where they intersect. But right, it's really, I feel like this is not super helpful, right? But I think this is kind of like, not so good. So scratch that. Here's what I want you to see with my not great pictures. The idea here, you know what? Why am I using not great pictures when someone else has drawn beautiful pictures? The idea here is that as we move this secant line to have a shorter and shorter interval, the slope of that secant line is getting closer and closer to the slope of the would-be tangent line. That's the really kind of big idea about finding the slope of the tangent line, is we're going to take the limit of the slopes of the secant lines. And that's kind of really it. So if we actually wanted to find the slope of the line tangent to the same function, x squared plus 6x, at the point 1, 7, what we're going to be doing is saying, well, this tangent line here, that tangent line is the limit of the slopes of the secant lines. So what we're going to do is, instead of picking like 1 to 2 or 1 to 3 or 1 to 3.5, we're going to let that second point be arbitrary. We're going to say, if I want to find, sure, time. Yeah, I got enough time. Barely, but I have enough time. So here's my other arbitrary points. And typically, ooh, you'd like to see what I'm doing typically. Typically, what we do is we say that this point is h away from the point we actually want. People use delta x sometimes, people use other things, but h is what most people tend to. And then this point up here, this y value, is going to be f of 1 plus h, whatever that is. So the slope of this, let's see if I can actually draw it nicely for once. Oh, look at that. It actually came out kind of nice. Kind of. So, I mean, that could look a little straighter there, but whatever. So the slope of the secant line, we already know how to find the slope of the secant line. It's the difference in the y values over the difference in the x values. And now what we're saying is the tangent line is more like that. That's going to be the limit of that same expression. But the limit as what happens? Well, the whole idea is I need to take a drink of water. The idea here is, right, is that we're letting this point move this way. So we're letting this get closer and closer, sorry, to that. And so as 1 plus h gets closer to 1, what's happening to the value of h? It's getting small. Or as I like to think about it, this difference here, which is h, that difference is getting smaller and smaller and smaller. So what we're doing is taking the limit as h approaches 0. And you might recognize that if you actually plugged in 0 for h, you would have a 0/0 expression. And that's why we've spent so much time practicing 0/0 limits, because they are the kind of limits you see when you do the limit definition of the derivative. Every derivative limit definition is going to, well, with some exceptions, most every one of them is going to be a 0/0 type of limit, which we're going to have to, do some work to evaluate. In this case, let's just do it. So the limit as h goes to 0, remember our function is x squared plus 6x. If I plug in 1 plus h, I'm going to get 1 plus h squared plus 6 times 1 plus h minus f of 1, which I know is 7, all over 1 plus h minus 1, which is h. Here's what's always going to happen with these types of limits. You're going to do some algebra, and after you do some algebra, the numerator should only have terms with h's in it. You factor out an h, and you cancel out the h in the denominator, because your ultimate goal is to get rid of that guy right there. He is terrible. We don't like you. We want you to get canceled. And the way we do that is by making sure that everything in the numerator that doesn't have an h also gets canceled. So if we do this, let's see what we get. I know it's 11:50, so we'll finish this example and then we'll be done. So 1 plus h squared is 1 plus 2h plus h squared. And then I have 6 times 1 plus 6 times h minus 7. And oh yeah, the 1 plus 6 minus 7, those definitely cancel out. So then I'm left with the limit as h goes to 0 of 2h plus h squared plus 6h all over h. And I suppose I could simplify that if I really wanted to, as a limit as h goes to 0 of h squared plus 8h. Right. But the important piece here is that each of them has an h. So you can either divide each thing by h, or if you prefer, you can factor out an h from the top. So I've got h times h plus 8 over h. And then those h's cancel like we wanted, right? We wanted that bottom h to cancel. And now I got the limit as h goes to 0 of h plus 8, which is just 0 plus 8, which is 8. So that tells me the slope of the tangent line at that point is 8. And if someone asked me to find the equation of the tangent line, because that's a frequent question people ask, we would say, okay, the equation of the tangent line is y minus the y coordinate equal to the slope times x minus the x coordinate. You might then solve for y, but you might also just leave it like that if you were out of time. Damn. Go ahead.
So typically when we're trying to find the slope of the tangent line, we're supposed to use the opposite side. This is not the case, right? Because we're using limits. So if we were finding
I think what you're talking about is the slope of a perpendicular line, which
because normally what we find so if we have like f of x equals to x squared plus 6x,
right.
we find the derivative of that and then equate it to 0, and that would be the slope.
I don't know why you're equating it to 0.
That's how, okay, maybe.
So because what you're talking about when you set the derivative equal to 0, you're finding where the function has a relative maximum or minimum. Right. So what I'm saying is this is definitely the long way. If I was going to do this the shorter way, which I know, so if you got to go, you got to go. I'll just say if I was doing this the shorter way, I know my function is x squared plus 6x. The short way of finding the derivative is, which we'll talk about next time. There's a lot of work to do to get there, but that's kind of the short way. And then you can find the derivative at the point of interest, which is 8. Yeah, so that's but again, right? So normally, here's what I'll say, last words. Normally, even with this limit definition, you wouldn't do it for a particular point, right? I would have actually normally said, if I want to find the derivative of this function, I would have said, okay, the derivative is the limit as h goes to 0. Instead of f of 1 plus h, I would have done f of x plus h minus f of x all over x plus h minus x. Because that'll tell me the derivative at any value of x, not just at the one value of x we're looking at. So yeah. But then if you do this, you do all the same sort of algebra we did up there, and you're going to get 2x plus 6 eventually. And then you can be like, oh yeah, then the derivative of 1 is definitely 2 times 1 plus 6, which is 8. I think that's what you're trying to say. All right, I should let you guys go because it's 11:54. It's definitely time to go.